Hi, let's begin our discussion on the concept of limit of a function. So let's start with some notation that keeps coming up when we discuss limit of a function. Here's a number line. You don't see the 0 and 1 on the number line because they're marked somewhere hidden away from you, but this is still the number line. I have this point, I have marked it as A. A is a number. So keep that in mind. A is a number, so it's a point on the number line. And now we're going to be seeing this kind of notation. X, arrow, that number, and a negative up here. We read this as X approaches A from the left hand side. So this negative has nothing to do with negative numbers or negative the way we use it in arithmetic. But this negative is a shorthand notation for X approaches A from the left hand side of A. And what that really means is the following. Any sequence of numbers x sub n, let's say we are looking at a sequence of numbers lying left of A. Every element of the sequence lies only on the left of A. So I'm just picking my sequence. So if I mark this as x1, remember x1 is a number because it's a point on the number line. Maybe this is x2. In any way I like, I'm just picking my sequence. And every element of the sequence is going to be to the left of A. And remember, this is an infinite sequence. I've only marked the first 3 elements of the sequence. Any sequence of numbers xn lying to the left of A, none of the xn is equal to A. So I cannot have any of these numbers actually on this dot, same dot as A. None of these numbers are A. And the limit of that sequence is A. So as I pick my points, the points should crowd A. And so X approaches A from the left hand side means this long sentence. The way I approach it is through a sequence of points, any sequence of points that lie to the left of A. None of them is equal to A itself, and the limit of that sequence is A. So when we discuss limit of a function, we'll regularly be looking at expressions like this. X approaches A from the left hand side. You'll see a negative sign there. Think of it in that manner. We're getting very close to A from the left hand side. Think of it as getting close to A as in the points of the sequence getting close to A. But we will never be at A because of the way I have described our notation. And when I write this, I always mean X is to the left of A, very close to A, but never at A. Very similar explanation for X approaches A. This plus means from the right hand direction. So this time I would be looking at a sequence of numbers lying to the right, and none of the elements of the sequence are exactly A, and yet the limit of the sequence equals A. So when I write this notation, X approaches A plus, that's really X approaches A from the right hand side, I mean it's any sequence of numbers lying to the right of A. None of the points is equal to A, and the limit of the sequence equals A. Okay. So intuitively you can think of this as a point very close to A, lying to the left of A, but never at A. X approaches A plus. You'll see when we do examples, we'll be considering numbers very close to A, right of A, but never at A itself. So keep that in mind as we move on to discuss the concept of limit of a function. Here I have the graph of a function y equals f of x. Recall the x-axis is a number line, the y-axis is also a number line, and I did not put the usual tick marks, but I did mark off a point and call it A. So A is a number. And now I want to discuss some notation that describes the behavior of the function for input values that are very close to A, but never A. In fact, notice for this function, we have this open circle here. That means that f of A is not defined. so we could not put a as an input into the function. But I want to find out what is the behavior of the functional values when we put in numbers in for x that are very, very close to a. So what that means conceptually is, we let the input value x approach a, say from the right hand side. So x approaches a from the right hand side. That's what the plus denotes. And remember, that really means a sequence of numbers where every number of the sequence is lying to the right of a, never at a, and the limit of the sequence is a. Notice for any sequence that you pick on that side with this kind of property, you could go up to the graph for every point here, x sub n. Now we can go up to the graph and look at this point whose x coordinate is x sub n and its y coordinate is f of that point, f of x sub n, and that f of x sub n, we could find it on the y-axis as a point or as a number on the y-axis. So what we are saying is, for any sequence that you pick here with this property, so every element of the sequence is to the right of a, no point of the sequence is actually a, and the limit of the sequence is a, then corresponding to that sequence, by going up to the graph and looking at the y coordinates, we can generate a sequence of like this, f of x sub n. And we ask ourselves, is there a pattern in those numbers? Is there a limit to that new sequence we created? That is really what we're asking when we say we want to look at the behavior of f of x for values of x very close to a. Now in practicality, when we are given a problem and we have to compute such limits, we don't actually look at sequences here and corresponding sequences there and so on. But once we understand this concept, we can actually compute limit of f of x as x approaches a from the right hand side in a more practical way. And this is the quick way of doing it. X approaches a from the right hand side. So we can pick a point that's very close to a on the right of a, and that point is never at a itself. And we go up to the graph and we look at its functional value. And as we can see, if we move our point closer and closer to a, its f value is going to get closer to L. Since we are never going to be at a, we don't need to worry that f of a is not defined. So from this picture, it's easy to see that the limit of f of x as x approaches a from the right hand side is in fact this value L. Very similar explanation for this limit of f of x as x approaches a from the left side. This is called the left hand limit. So we look at points very close to a, left of a, and that point is never at a itself. Go up to the graph and you can see that's a point close to L, and the closer you get to a on the x-axis but never at a, you can see its functional value gets closer and closer to L. And so this is the notation of it. So in this scenario, f of a is not defined, but even so, the right hand limit, which is limit of f of x as x approaches a from the right hand side, is L. The left hand limit, limit of f of x as x approaches a from the left hand side, is exactly L. And we will now discuss what it means to say limit of f of x as x approaches a. We'll put together these two pieces of information and come up with a definition now. So here's the definition. Suppose f is a function and a and L are two numbers. We say limit of f of x as x approaches a is the number L if both of these are true. Limit of f of x as x approaches a from the left is L, and limit of f of x as x approaches a from the right is also L. So if both the right hand limit and the left hand limit exist and they're exactly the same number, then in that case we say that the limit of f of x as x approaches a exists, and it is that common number L. Notice in particular, no mention is made about f of a. So the function may be defined at a, may not be defined at a. Nothing is mentioned about that. So in other words, to talk about limit of a function as x approaches a, we do not need to worry about f of a. X approaches a means we consider both scenarios. X approaches a from the right side, x approaches a from the left side, but we never ask x to be at a. So if the left hand limit and the right hand limit exist and they're equal, then the limit of f of x as x approaches a exists, and it is this common number. So let's go back and look at the example we were discussing. So back to this example where we said the right hand limit and the left hand limit for this function exist and they're equal to L. So from the definition that we just went over, this implies that the limit of the function as x approaches a exists, and it's equal to this common value of L. Notice that that is so even when f of a is not defined. Now let's look at this example. So this is same as the previous example, except here I have in fact added this on one more point to the graph. So f of a is now this point. Even then, nothing changes. Limit of f of x as x approaches a from the right hand side is still L. The fact that f of a is now defined and it's this point, it does not affect this, it does not affect this, and it also doesn't affect this. So all of these three facts are still true for this example where f of a is now defined and it is this point. And now for this final example, this is just a small modification of the previous example. These answers still hold true. In this case, L is in fact exactly same as f of a. F of a is now defined. But the point I want to make is limit of f of x as x approaches a. If you want to compute that, first compute the right hand limit and the left hand limit. If they both exist and they take on the same value, then by definition this limit exists and it is that same value. In the next video, let's look at examples where the graph of the function is given and we will compute this, this, and this. Thank you.